My name is Royal Valdez, and today I'll be presenting the Andrew file system, a revolutionary approach to share data. The content presented today will be general history of the Andrew file system, the understanding of a local file system, the development, efficiency and performance, its architecture, support, security, correction, handling, and a comparison between distributed and parallel file systems. The objectives will be to provide an explanation on the development of file system, provide advantages and disadvantages, compare and contrast the Andrew file system to other contemporary file systems, to give a high and low level explanation of the Andrew file system architecture, and leave the viewer with a general understanding of the AFS. Some background, our setting takes place from the early 1970s to the late 1980s. In the 1970s, personal computers were introduced to the consumer market and were very popular. Manual office tasks were beginning to get replaced with computer programs such as spreadsheets, emails, Word documents. Also, floppy disks were the primary device used for transporting and sharing personal data. Through the 1980s, data became more crucial to everyday life, and the development of powerful microprocessors also happened. Computers gained the ability of connecting to one another. Various distributed file systems were developed. Before we go into what a distributed file system is, it's important to understand what a local file system is, since they overlap. Local file system is essentially a tool which is a subcomponent of the operating system. This tool controls how data is stored in a secondary storage device, which allows the user and programs to modify data by abstracting the background work that must go on. We can break down the file system into architectural layers, which has logical, virtual, and physical layers. The logical layer is a level in which the user can request for operations by using system calls like open, close, read, and more. It also passes the request down to the layer below for processing. The next layer is the virtual layer. This layer allows support for multiple concurrent instances of the logical layer. The physical layer is responsible for physical operations of the storage device, such as read and write of a physical block and their placement in a specific location of the storage device. We also have space management. This includes details such as which part of the memory are free and how large they are. Bitmaps can be used for this kind of purpose. The permissions, who is able to read and write, basically modify the file. Data integrity, make sure the data is not corrupted if it is being used by multiple processes or is being modified. Without the file system, application development would not be pleasant, since finding a way to manage memory would have to be taken in consideration each time. This could lead to having different programs manage memory differently, and possibly causing corruption in the data. Some disadvantages of file systems is that they have very limited storage, since it's basically your local storage, your secondary device storage. It's not easy to share with someone else, and it has limited collaboration. The advantages is that it allows programs to interact with data easily. Also, Windows, NTFS, and FAT32 existed, and Linux extension 2, 3, and 4 existed as local file systems during that time. Now we can talk about the distributed file systems, now that we understand what a local file system is. Essentially, a distributed file system is the same as a local file system, but for cloud. It allows multiple clients and transparency. Multiple clients meaning that multiple workstations can be on the network downloading or accessing files and editing them as well. Transparency meaning that the Andrew file system would appear as a local file system, causing less of a learning curve on the user. Various groups at the time were developing different variations of DFS. Some microsystems created the network file system, NFS, from the late 1970s to mid 1980s. The University of California, Berkeley, worked on Sprite DFS from 1984 to 1992. Sun Microsystems DFS had some limitations. To not get too much into detail, one of them was users had to know the physical address of every computer involved in file sharing. By the mid 1980s came the Andrew file system, providing a different approach. The Andrew file system development started in 1982 at the Carnegie Mellon University with an IBM partnership. The name came after Andrew Carnegie and Andrew Mellon, the founders of the university. The goal was to support the growth of at least 7,000 workstations on the campus, so that students could go from one workstation to another and access the same files without noticing any performance issues. They also wanted to use high functional workstations running Unix. The network consisted of a mixture of Ethernet and token rings tied by bridges with a hierarchy organized topology. In this image to the right, we can see the ring topology here, the bridge, and the Ethernet. Files were the basic unit of data movement and storage. Essentially, nothing would be downloaded by pages, it would just be an entire file. It was less of a strain on the network. It would also be downloaded to a local disk so that the user could work locally, and then once it was done using it, it would send it back to the server. It was implemented on many relative small servers, 50 to 100 workstations per cluster, 100 clusters in total, and closely resembles a standard Unix file system. Vice and Virtue are essentially just nicknames for the client and the server. Vice is the server, Virtue is the client. AFS goals: location transparency, user mobility, security, performance, scalability, availability, integrity, and integrating new types of workstations without causing any kind of problems in the network. Just to lightly hit on some of these, transparency: files on a server should be able to have one namespace for all the shared files in the system. The naming scheme should not have any relations to the location of the files. The user mobility: users should be able to access files in any shared namespace from any workstation on campus, and the performance should not discourage users from using the system. Scalability: the growth of the system should not affect other workstations. So AFS efficiency and performance. Essentially, it breaks down into caching and whole file transfer. Caching is the main form of replication in the AFS design. Replication is a key strategy for improving reliability, fault tolerance, and availability in distributed systems. Components in distributed systems can fail independently. Using replication algorithm, AFS is able to make a file more available in the case of failure in the server. Local files are the files that the user leaves on their local machine. Cache files are files that the user has used through the Andrew file system. These are cached in order to maintain the server overhead minimal. Cache files from Vice. Caching reduces potential and centralized resources. Virtue has two parts: a set of modifications to the workstation operating system to intercept file requests, and a user level process called Venice. Venice handles the management of the cache, communication with Vice, and the emulation of native file system primitives for Vice files. Venice uses LRU cache management algorithm, using a local directory on the workstation. It limits the number of files instead of cache size, since it was difficult to know at the time in a Unix system. When a workstation opens a file in the shared namespace, Virtue finds appropriate custodian and stores the file in the Vice cache section of the workstation. Individual read and writes are directed to the workstation cache copy. Upon closing the file, if any changes were made to the file, it will be sent to the corresponding custodian. Vice supports read-only applications of subtrees at different cluster servers. The idea behind this is to be able to balance server loads by grouping subtrees that rarely get modified. Essentially, files that are not modified a lot are together so that there's less strain on the network and on the servers.
Hello, my name is Ted, and we are going to be talking about the basic architecture of the Andrew file system. So let's get into it. So you can logically divide it into two subspaces, vice and virtue, although they are very much subdivided as well. So virtue is the nickname for each individual client workstation, and it runs a process called Venus, which authenticates clients and aids in local disk caching. It's connected to Vice via an unsecured connection, so they use encryption to communicate between the client and the server space. Vice is the nickname for the actual server space. It does not encrypt traffic between the servers. And we're going to talk about it at length here right now. So more on Vice. Over the years, it has expanded to mean a network of servers and their processes, excuse me. The server supports several crucial processes. So the basic overseer server, the volume location server, the volume server, protection server, salvager, the update server, and backup server. And we're going to get into all of those. So here's actually a diagram, two diagrams rather, from the original paper, the ITC Distributed File System, co-authored by Dr. Satya in 1985. So as you can see over here on the left, you have Vice, which is a network of servers essentially, and Virtue being the client workstations. And then over here on the right kind of shows you how the LAN is configured as well. So the basic overseer server, aptly, it is pronounced the boss server, and it acts, as the name suggests, as an overseer for all processes running on the servers. So this will restart any failed processes without administrator intervention. It's programmed to restart certain processes in a particular order if more than one of them fails. It provides a basic interface for the administrators, and it will apprise the system administrator of the status of a process and will accept commands from the administrator to start and stop processes. And it also adds and changes server encryption keys. The volume location server, the VL server, maintains a list of volume entries in the volume location database, the VLDB. The cache manager communicates with the VLDB server to find the correct file server for any file that's requested. And regarding the VLDB, this maintains entries for every volume of a cell, which is just a name that they use for an independently administered site. Contains all volume metadata as well. So volume name, volume ID number, permissions, number of sites that houses the volume, and a list of those sites. And then it will inform the cache manager the location of the requested file. The protection server is for security purposes, as the name suggests, and this will define 7 permissions as opposed to Unix's 3. So the administrator permission, delete permission, insert permission, lock permission, lookup permission, and then we all know what read and write does, but the aforementioned ones are all very self-explanatory. Allows admins to grant permissions to users as well. So here's an example of how you'd actually retrieve the volume metadata using the CLI. You would use the VOS examine command, and then as you can see down here, you can see your number of sites. Under that is where that site is. You can see that the volume is locked. So this is actually taken straight from the user manual for AFS. The volume server, it provides the interface for creating, deleting, and moving volumes. Volume moves are conducted here to enforce load balancing. And volumes are also replicated and distributed to multiple file servers. So a volume is actually the basic unit of replication in AFS. So you're going to replicate by volume. It's taking any read or read-write file and cloning it to read-only. And the volumes are replicated to assist in efficiency. So because of this, more than one file server can help with any file request. And then any read-write volume can be replicated, although they do advise that you stick to typically read-write files that are usually often not altered and are very popular. So a bit more on replication. Replication is typically conducted in 4 steps. You ensure the current administrators on the user list file. Second, select the site to house the replication, and this is done using the VOS examine command that we just looked at. Use command VOS add site. This actually adds the site where you're going to be housing your newly replicated volume. And then the command VOS release with the volume ID will actually create the read-only clone for the volume. And it's noted down here, as I just mentioned, administrators replicate highly requested files that aren't altered often. The protection server, users can define their own groups of users. So because of this, you can grant blanket permissions to entire groups. And a system administrator may also create groups based on client IP addresses, and this is to enforce licensing restrictions, and it will also convert usernames to AFS IDs, which is typically what is used in the server space. So the salvager, this does not run all the time. It only runs when it's invoked by the boss server, or you can manually invoke it if you're an administrator, and it serves as an assistant. The boss server invokes the salvager when the file server, volume server, or both fails. And you can see here, this is the BOS salvage command. And down there where it says parallel, you actually choose an argument of 1 to 32, and that is how many sub-processes you would like to run on the salvager. So you got a lot of control there. Oops. The update server maintains consistency regarding the version of the file server that's running. And the binary distribution machine, that's software that goes on one file server. And the update server will periodically check that to ensure that you're working with the latest version of the file server process. And it also is responsible for distributing system configuration files. And it works kind of just like the binary distribution machine. So you need to update one system configuration file, and then which is found in the system control machine, and then the update server will automatically update the file to align with the system control machine. Binary distribution machine or the system control machine can be checked using this command, BOS status, and then the machine name, and then the following. And this will return output based on which kind of machine was contacted. The backup server, this is its own beast. There is quite a bit to it, and we need to move on to the file server, but just a basic overview, maintains the backup database, BUDB. The backup server and BUDB together are called the backup system. It is the only way to backup AFS, and administrators choose volumes to aggregate and then write them to a disk. And it itself is actually backed up in case it's corrupted. So all these files actually have to be served somewhere, and that's the file server. So they use file server machine to sort of describe any of the previous processes. And then there's the actual file server process, which is what we're discussing currently. So every file server machine has a file server process. Services requests from clients for files, and it stores the correct version of the file when it wishes to write. Maintains the directory structure and the metadata, so file ID, time of creation, size of file, last modification time, permissions, and site. And then all of the metadata is locally cached on client workstations by the cache manager. Symbolic links are used, so the operating system assumes system files are stored locally. However, what they've done is created symbolic links. So any symbolic links can redirect references to such files, the system files, to AFS share files. And this actually frees up a lot of space on the local disk. So that's why they went that route. And it'll grant advisory locks as well. Regarding consistency, that is mainly the job of the file server and cache manager. The cache manager stores files in their entirety on local disk in a default block size of 64 kilobytes, and the default block size can be manually changed by an administrator, and they use what's called a callback, and this is a term native in AFS, and it actually was started when AFS version 2 was used, when Dr. Satya noticed that the test auth, so that was the protocol used to check whether or not somebody is working with the latest version of the file, was taking up 67% of all system calls, so they devised a new way to scale back the network traffic. So it's only used when a user writes to a file, and this prevents any necessary network traffic, as I just said. V files are files that house the 64 kilobyte blocks. When the cache manager initializes checks to ensure that it has the number of V files that is the largest of the following. So either 100 cache size divided by chunk size times 1.5, cache size divided by 100 megabytes. If there are fewer V files than the numbers above, the cache manager will auto-create new ones. And if there are more than needed, the cache manager will deallocate the extra space. So pretty handy. And any file larger than 64 kilobytes or the set chunk size will be divided amongst multiple V files.
My name is Austin Wynn, and I'll be going over the support, security, corruption handling, and comparisons for the Andrew file system. The Andrew file system was a project developed to be a distributed computing environment in the mid-1980s. In the original design, there were big flaws that obstructed scalability. One of the flaws being the overhead of file changes. The file server would then have to keep trying to see if the file was updated. That caused a lot of overhead, and it limited the number of clients that a file server could take on and do requests to, because after 20 clients, the file server CPU utilization would be at 100%, so no more clients could be taken. Another issue with this is that the load wasn't balanced, so only one file server would be at 100% CPU utilization while another wouldn't be. These were later fixed with the implementation of volumes and callbacks. In the 1990s, the Andrew file system was broken off and commercialized by the newly founded Transart Corporation and was ported to Linux. And as of today, the Andrew file system is still in current development, open source, and is supported by multiple platforms, including Linux, Mac OS X, and Windows. Authentication and protection servers. The authentication server maintains the authentication database, which stores user passwords and server encryption keys. It uses Kerberos to deploy the mutual authentication between clients and servers. The protection server is a key component in the implementation of access control lists. It maintains the protection database, which stores all access control list permissions info for each directory. The Andrew file system uses Kerberos Key Distribution Center, KDC for short, for user authentication. Kerberos has multiple features. Users must enter a password when logging into a realm or running programs. This creates a ticket. The ticket is then converted into a token that processes use to validate the user. The token system also allows users access to remain available for approximately a day, 24 to 25 hours. And it uses dual authentication so that both the client and server's identities are validated against each other. One Kerberos KDC can provide an authentication realm for multiple cells. With this being the case, you can have users that have permissions within multiple cells. Kerberos 4 was a previous version of Kerberos and had several vulnerabilities, including a privilege vulnerability where an attacker could use a plain text attack to elevate its privileges, which would allow them access to all directories and all files so they could corrupt or otherwise harm the system. Since then, Kerberos 5 has been introduced and those issues were fixed. The Andrew file system uses access control lists to control users' access to data. Access control lists have features unlike traditional file systems where files individually have their own permissions of read, write, etc. Access control list gives permissions to the users at the directory level, given the 7 access control list permissions given before. Administrators can easily administer access and remove access to the users also. And a special thing about access control lists is that it can be created for groups of users based on the credentials in the protection database, or it can be based on groups of IPs for client computers. To keep an accurate backup protection and volume location database, all of these servers have to be in sync. This is the job of the Network Time Protocol daemon, the NTPD. One server, this can be inside or outside of the cell, obtains time from an outside source, an outside time server, and is represented to the cell as the central time server, so that all inside servers can be synced together based on one server. Each database runs the NTPD, which gains the time from this central time server so that all of the data is up to date relative to the system, and all volumes can replicate the same data, etc. Another form of data protection from corruption is local caching and callbacks. With this, the file server sends a copy of the file along with a callback and the file server will break the callback if a file is updated while someone else has the file open or in their cache. Volumes can be moved transparent to a user if a drive fails or is corrupted. So without the user knowing, an administrator can move a volume from one server to another at their discretion. In this slide, I will be presenting an example of the callback system. Here we have client A, client B, file server A, file server B, and the volume location server. So here, client A is requesting research.docx. The volume location server will then respond with the file server that is closest and most accessible to client A. Then client A's cache manager will send a remote procedural call to file server A. And file server A will respond back with the file and a callback linked to that file. Once the file reaches client A, the cache manager caches it locally and then sends it to the application that requested it. Now let's say client B wants to access the same research.docx. The volume location server gives client B the file server to go and get the file from. So client B's cache manager sends a remote procedural call to file server A. File server A responds with the file and a callback. And then client B caches the file locally and sends it to the application. Now in this instance, client A and client B are both having their own separate copies of research.docx. Now let's say client B finishes and they save their changes, which updates the file at the file server. This causes client A's callback to be broken, meaning that client A has an old copy of the file and it needs to be updated. Now I'll go over the differences between distributed and parallel file systems. The main difference between distributed file systems and parallel file systems is that parallel file systems are geared more towards high performance computing and parallelism. The distributed file system is more towards high scalability. It takes on fault tolerance and resource sharing. A distributed file system is loosely coupled, meaning that software and hardware are independent of each other, so that if hardware fails, the software will still continue to run as normal. This is because distributed file systems use replication or methods such as erasure techniques to maximize system redundancy. Parallel file systems, on the other hand, are used more for high performance computing applications. They're tightly coupled, which means that the software and hardware are dependent of each other, meaning that the more hardware, the better the system will perform. Usually includes simultaneous access from multiple compute servers, which can be coordinated from the software, and is often used in machine learning, AI, video editing, and visual effects rendering. Andrew file system has its advantages, those being great performance due to its local caching, volume location transparency to the user, which creates an efficient fault-tolerant environment. It's highly secure due to Kerberos, and access control list makes access management easier for network administrators. Andrew file system also has its disadvantages, that being low performance with high read-write files, and it had early limited platform options, which caused its adoption to be lessened historically. However, it does have great adoption in large institutions now, and it is in open source current development. Therefore, it will continue to be a great file system for years to come.